We're going to continue our discussion of colligative properties by looking at some other ones that are related to vapor pressure lowering. So that vapor pressure lowering is going to occur at all temperatures. And so if we think about boiling, boiling happens when the vapor pressure of the solution equals the atmospheric vapor or atmospheric pressure. And so it's because the vapor pressure of the solution is lower than the vapor pressure of the pure solvent, the boiling point is going to be higher for the solution than it is for the pure solvent. The freezing point is also affected. The freezing point of the solution is lower than the freezing point of the pure solvent. So basically the solution is more stable in the liquid form, and so the freezing point is decreased and the boiling point is increased. You see this all the time in the winter with ice melt. You know that salt is dumped on the road in order to essentially melt the ice. What's happening is you're forming a solution of salt and water, and then that has a lower freezing point than pure water, and so it puts it back into the liquid phase, making it less slippery up to a certain point. So there is if you look at my table here, effective temperatures differ depending on what the salt is that you're dumping on the road. Here's a picture of what's happening. So basically, by lowering the vapor pressure, we're shifting the lines here in our phase diagram down and to the left. And so we lower our vapor pressure, lower our freezing point, and increase our boiling point by a certain amount, which we will talk in a minute about how to calculate. The equation for figuring out the change in freezing point is going to be the change in your freezing point is the molality of your solution times this Kf value, the freezing point depression constant. And the one for boiling point, again, the change in boiling point is going to be the molality of the solution times the boiling point elevation constant. Table 12.8 in your textbook has constants for some liquid solvents, common liquid solvents. And again, it's a delta T. So to figure out the new freezing point or new boiling point, you have to shift your temperature by that much. So let's work through a problem. What is the freezing point of a 1.7 molal aqueous ethylene glycol solution? So we know that our delta T is going to be the molality times that freezing point depression constant. It's an aqueous solution, so we want our Kf for water. If I look back in my table, the Kf is 1.86 degrees Celsius per molal. And that's all I need to solve this. So my change in freezing point is going to be 1.7 molal solution times 1.86 degrees Celsius per molal. So my change in freezing point is 3.16 degrees Celsius, which means my new freezing point is going to be negative 3.2 degrees Celsius because there I'm just taking my normal freezing point 0 minus, because it's freezing point depression, 3.16 gets me negative 3.16, and then for sig figs, I'm down to 2 of them. So you can see the solution there. Let's work through a different type of this question. Calculate the molar mass of a compound if a solution of 12 grams of that compound dissolved in 80 grams of water freezes at negative 1.94 degrees Celsius. So here I know that my delta T is equal to my molality times my Kf value. Remember that molality is moles of solute divided by kilograms of solvent. And I don't know my molar mass of my solute. But I can solve this for my molality. I know my grams of solvent. I can find kilograms. Then I can find my moles. Then I can take my grams divided by my moles to get my molar mass. Okay, so let's work through that. Negative 1.94. Actually, this is just going to be 1.94 because it's a delta T. So 0 minus negative, 0 minus something is negative 1.94, so the something is 1.94, is equal to my molality times my Kf, 1.86. So I can solve for my molality is 1.043. And then again, now my 1.043 is equal to my moles of solute divided by 80 grams is 0.080 kilograms of water. And so my moles of solute is 8.344 times 10 to the minus 2. And then I have 12 grams is my 8.344 times 10 to the minus 2 moles. So my molar mass, grams per mole, is 144 grams per mole. Again, this table has the boiling point data as well as the freezing point. So the way it works is essentially the same, except remember, boiling point is elevated, whereas freezing point is decreased. And so when you use the boiling point one, you're going to add whatever you get to the boiling point, whereas you subtracted it from the freezing point. And that's just something you have to memorize. It doesn't show up directly in the formulas. All right. Another practice question. Lauryl alcohol, a component of coconut oil, is used to make detergents. A solution of 5 grams of lauryl alcohol in 0.1 kilograms of benzene freezes at 4.1 degrees Celsius. What is the molar mass of lauryl alcohol? The Kf of benzene is 5.12 degrees Celsius per mole, and the normal freezing point of benzene is 5.50 degrees Celsius. So I would recommend pausing the video and working through this, and then coming back to check your answer. So we know that our delta T is the molality times our Kb here. So our delta T is going to be 5.50 minus 4.1 is equal to our molality times our Kb of 5.12. So we can solve for our molality, which is 2.73 times 10 to the minus 1. And then we know also that our molality is our moles of lauryl alcohol. divided by our kilograms of solvent, which we're given is 0.100 kilograms. So we can find our moles of lauryl alcohol is 2.73 times 10 to the minus 2. And then we know that 5 grams of that is this many moles. So if I take my 5 divided by 2.73 times 10 to the minus 2, I get an answer of 183 grams per mole. Okay, here's another practice for you. Again, I would recommend pausing, working it through. What is the freezing point of an aqueous solution that boils at 106.5 degrees Celsius? And my Kf for water is 1.86 degrees C per mole, and my Kb for water is 0.512, and those just come from the table. Okay, so if my solution is boiling at 106.5 degrees Celsius, that means that my delta T is 6.5 degrees Celsius is equal to my molality times 0.512 degrees Celsius per mole. So my molality is 12.695 mole. Then I can plug that in. So my delta T for my freezing point is my 12.695 times 1.86. So my delta T for my freezing point is 23.6 degrees Celsius. So my new freezing point is negative 23.6 degrees Celsius. Here's another practice. What mass of calcium chloride would you need to add to 100 milliliters of water to bring the freezing point down to negative 32 degrees Celsius? And again, my Kf for water is 1.86. And one other thing to know, when calcium chloride dissolves in water, you're going to get 3 particles. So this question involves something that we're going to talk about in lesson 8 in a couple videos, and that is the fact that you need to account for the number of particles in colligative properties, not just the overall concentration. So here, my delta T is going to be the molality times my Kf times what's called a Van Hoff factor, the number of particles that it's breaking up into. In this case, that's going to be 3. So my equation is going to be 32 is equal to my molality that I don't know times 1.86 degrees Celsius per mole times 3 for the 3 particles that calcium chloride breaks up into. So then I can solve for my molality, and I get a molality of 5.73 mole. And then I have that times my 100 milliliters of water at 1 gram per milliliter, converted over to kilograms, is 0.100 kilograms of solvent. That gets me 0.573 moles of calcium chloride. Then I can take my 0.573 moles times 1 mole, and then my molar mass, I have a dihydrate, so I need 2 water molecules plus my calcium plus 2 times 35.45 gets me 83 grams of calcium chloride dihydrate.